In this video, we're going to dive into practicing inelastic collision problems. When you are tackling any inelastic collision, there's one crucial tool you need in your toolbox. It's the law of conservation of momentum. It's actually pretty straightforward. The total momentum before the collision has to be equal to the total momentum after the collision. And that's it. Momentum is always conserved, even in these messy collisions. But you need to be careful here. There's a very common mistake. The mechanical energy is not conserved during an inelastic collision. When two objects crash together, they often deform, they make noise, and they might generate some heat. And all of that means some of the mechanical energy is transformed or lost from the system during that collision process. You cannot use energy conservation for an inelastic collision. Only the momentum is conserved. Okay? Alright, now that we know the basic rule, the momentum is conserved, let's put it into practice with an example. Imagine we have two space probes being tested in a robotic lab. And probe A is flying straight east, probe B is flying straight north. When they smash into each other, they are not bouncing off. They are going to stick together and become one combined mass. And that tells us right away that this is a perfectly inelastic collision. What happened after the crash is this combined mass or these coupled probes will move at a speed of 15 meters per second in the direction of 28 degrees east of north. And our job is to figure out what were the initial speeds of probe A and probe B before they collided. We've established our key equation where the total momentum before the crash equals the total momentum after the crash. Then how do we apply this equation? Well, the first thing you need to realize is that this collision is happening in a two-dimensional space. So we cannot apply it directly. We need to apply this law twice, once for each direction. First, we'll focus on horizontal motion. We'll set up one equation to conserve all the momentum pointing east and west. Okay, and that's our x-axis. And then separately, we'll set up a second equation to serve all the momentum pointing north and south. And that's going to be our y-axis. So instead of trying to use p before equals p after all at once, we've essentially split it into two equations. For the x direction, we should have p before in x direction equals p after in x direction. And for the vertical direction, we have p before in y direction equals p after in y direction. Let's work on them one at a time, starting with the x direction. To keep all our variables straight and easy to track, let's create a simple table focusing entirely on the momentum in the x direction, or px. We need to find the momentum before the collision and after the collision. And before the collision, we have two separate objects. It's probe A and probe B. And we need to find the momentum for each of them. And after the collision, the two probes combine into a single object. Let's call it probe A and B. Momentum is just the product of the mass and the velocity of the object, right? So for every row in our table, whether it's before or after the collision, we'll find the mass, find the velocity component in the x direction, and then multiply them to get the momentum in the x direction. Now let's start filling in the details before the collision. For probe A, we'll call its mass ma, and the problem tells us that ma is 800 kilograms. Now let's look at the velocity vax. Because probe A is moving directly towards east, or purely along x-axis, so its velocity along the x-axis is simply va. So this is the unknown we are solving for. Therefore, the initial momentum of probe A in the x direction is the mass ma multiplied by vax, which gives us 800 va. Alright, now let's move on to probe B. Let's call its mass mb, which the problem gives us as 580 kilograms. Now let's look at its velocity in the x direction, vbx. We know probe B is moving directly north, which is purely along the y-axis. This means the probe B has no horizontal motion, and its x component of the velocity, vbx, is 0. The initial momentum of probe B in the x direction is mv multiplied by vbx, which equals 580 kilograms multiplied by 0, which of course gives us 0 momentum. Okay, now we turn our attention to the momentum after the collision. Since the two probes stuck together, they form a single object, and the final mass is simply ma plus mb, and that's 800 kilograms plus 580 kilograms, giving us a total mass of 1,380 kilograms. Now, the crucial part is the final velocity's x component. Let's call it Vx. We know the combined object is moving at 15 meters per second at an angle of 28 degrees from the north. To find the x component of this velocity, we need to use the trigonometry. If we draw a right angle triangle, the speed v is the hypotenuse, and vx is the side parallel to the east direction. Okay, and the angle 28 degrees is measured from this vertical axis. And in this triangle, Vx is the opposite side to the 28 degrees angle. Therefore, to find Vx, we use the sine function. We have Vx equals V multiplied by sine 28 degrees. Plugging in the values, we have Vx equals to 15 multiplied by sine 28 degrees, and that calculates out to approximately 7 meters per second. So the final momentum in the x direction is the total mass, ma plus mb, and then multiplied by its final x velocity, vx. And this gives us 1380 kilograms multiplied by 7 meters per second, which equals to 9660 kilograms meter per second. So the total initial momentum before the collision in the x direction is the addition of the momentum from probe A and probe B. And that's actually 800 VA plus 0, which equals 100 multiplied by VA. And the total momentum after the collision is simply 9,660 kilograms meter per second. Now we have all the pieces we need for the x direction equation. We apply the law of momentum conservation in the x direction. So the total momentum before the collision, which was 800 multiplied by VA, must equal the total momentum after the collision, which was calculated as 9660 kilograms meter per second. Then we can easily solve for VA by dividing the final momentum by the mass. And this calculation gives us VA equals approximately 12 meters per second. So before the collision, probe A was moving at 12 meters per second towards east. We found the initial speed of probe A. Now all we need to do is to repeat these exact same steps for the y direction. You've probably already guessed it by setting the total momentum before the collision equal to the total momentum after the collision along the y-axis. We'll be able to solve for the initial speed for probe B. Now let's review this table to find the momentums in the y direction. For probe A, its mass, ma, is still 800 kilograms. However, this time, because probe A is moving directly east or purely along x-axis, it has no vertical motion. So its y component of the velocity, Vay, is simply 0. Then we have the initial momentum for the probe A is ma multiplied by Vay, which equals to 800 kilograms multiplied by 0. So probe A has the initial momentum of 0. For probe B, its mass mb remains 580 kilograms, and probe B is moving directly north before the collision, and this means its entire speed is its y component, right? So we have Vby equals Vb. Then the initial momentum of probe B in the y direction is mb multiplied by the velocity in the y direction, Vby. And this gives us 580 multiplied by Vb. Now after the collision, the final mass is the same as before, which is ma plus mb, which equals 800 plus 580 kilograms. So the combined object's mass is still 1380 kilograms. Next, we need to find the final velocity's y component, Vy. Now let's look back to our right-angled triangle. The y component of the final velocity is the vertical side of this triangle. It's the adjacent side to the 28 degrees angle. So Vy equals V multiplied by cosine 28 degrees. And we have V is 15 meters per second, and then multiplied by cosine 28 degrees. This gives us Vy approximately 13.2 meters per second. Then we have the momentum equals ma plus mb, then multiplied by Vy. This gives us 1380 kilograms multiplied by 13.2 meters per second, which equals to 18,216 kilograms meter per second. So the total momentum in the y direction before the collision is simply 0 plus 580 VB, or just 580 VB. And the total momentum after the collision is 18,216 kilograms meter per second. Now we apply the law of momentum conservation for the y direction and set the equation. The total momentum in the y direction before the collision is 580 VB. It equals to the total momentum after the collision, which is 18,216. We can quickly solve for VB by dividing the momentum by the mass. And this calculation gives us VB equals to approximately 31.4 meters per second. So before the collision, probe B was moving at 31.4 meters per second toward north. So to quickly recap everything we've covered, for an inelastic collision problem, your essential tool is the law of momentum conservation. If the problem involves motion in 2 dimensions, then all you need to do is to apply this law separately, once for the x direction and once for the y direction.